Monte Carlo problems are usually classified as either integration or simulation. So, we'll be concerned with simulating experiments in physics. Now, this begins with a theory or hypothesis about the physical process. So, most likely with an assumption of an underlying probability distribution function. Which may then get modified by the response function of the experimental apparatus. So the expected PDF of the observations is given by integration over gx prime times the response function integrated over all such x primes. Now, the purpose of the simulation is to produce a set of n simulated or fake data points distributed according to fx. These can be compared with the real data to test the hypothesis. They can also be used in the planning stage of the experiment to help in its design. For example, to compare the use of different apparatus and to test software to be used in the analysis of the experiment. Since these fake points are distributed according to fx, they are in fact just the points generated for the Monte Carlo integration of fx. So simulation is formally at least equivalent to integration. But it's the purpose which is usually different. So that's why often a different Monte Carlo method will be preferred for simulation than for integration. Now the PDF that we wish to simulate, that is fx, this can be extremely complicated. So the underlying physical PDF which is denoted by this g of x prime. This itself can involve integrals which will be evaluated by Monte Carlo in the course of simulation. Also, the detector description may consist of various stages, each depending on the previous one. So the Monte Carlo simulation of such complex processes breaks them down into a series of steps. And at each step, a particular outcome is chosen from a set of possible outcomes according to a given PDF, fx. In other words, the outcome of the step is a pseudo-random number generated according to fx. But random number generators generally produce uniformly distributed numbers. So we must transform the uniformly distributed random numbers into random numbers distributed according to the desired PDF. And there are a few basic methods to do this. First is the method of weighted events. So this is analogous to the crude Monte Carlo for integration. So for a PDF, fx defined on an interval a comma b, points are generated uniformly in X and given a weight W. So an event in that case consists of the values xi and wi, which are basically f of xi times b minus a. The integral of fx over any subinterval of a comma b, let's say c comma d, where c is greater than a, less than d, and d is less than or equal to b, is then given by the sum of the weights of the events in that interval. So basically, this integral from c to d is given by 1 by n. In particular, a weighted histogram of the xi, where c and d would be the various bin limits, represents the PDF and can be directly compared to the data. We have seen that integration by crude Monte Carlo gives a smaller variance than the hit or miss method and is generally preferable. But in simulation, it is usually deemed preferable not to have weighted events, because one prefers to have the Monte Carlo events as much as possible like the real events. So it's desirable that the Monte Carlo sample behaves statistically like the real event sample. For example, the variance of the average of n Monte Carlo points should result in the same variance as that of the average of n real points. This is not the case with weighted events. The density of the Monte Carlo points where fx is small is same as where fx is large, whereas in the real data the density of points is proportional to fx. Now, speaking of the hit or miss method of Monte Carlo integration, the next method is the rejection method. So just like in the hit or miss Monte Carlo, we generate points uniformly in X as well as fx. So xi is the randomly generated variable from the interval a comma b. Ri is the randomly generated variable between 0 and f max. F max is the maximum value of fx within a comma b. And then points for which f of xi is less than that random number ri are then rejected. And an integral over a subinterval c comma d is given as So in hit or miss Monte Carlo, we also had an f min or y min, if you want to speak in the language we had used there. Since we knew the integral from a to b for f min dx, it was not necessary to evaluate it by Monte Carlo. It was therefore better to use all the Monte Carlo points to evaluate f minus f min dx integrated between a and b. But here we want to generate all the events for f, not just for f minus f min. So the difficulty lies in knowing f max. If we do not know it, then we must guess a safe value. That is a value which we are sure is larger than f max. If we choose f max too safe, the method becomes inefficient. The method can be made more efficient by choosing different values of f max in different regions. Now, next we have the inverse transformation method. So let's first look at the case of continuous PDFs. Now this method is like importance sampling with gx equals to fx. The resulting integrand is the uniform distribution. We transform from fx to capital F, where capital F is nothing but the CDF of small f. The cumulative distribution function. Now, instead of generating points uniform in X, we generate points uniformly distributed in capital F between Fa and Fb, which are 0 and 1 respectively. So, if Fx is a PDF normalized on a comma b, in ui is a random variable picked from the interval fa to fb. Then we calculate the corresponding value of x. It's the f inverse of ui, and these xi's are then distributed as fx. To see this, we call the results on changing variables. So for a transformation u to x given by some v of u with inverse transformation u equals w of x, the PDF for x is given by the PDF for u times the Jacobian. So PDF for x equals g of u, which is the PDF for u, times del u by del x mod, or in other words g of w of x del wx by del x. Now here u is nothing but capital F of x, which basically means x is f inverse of u, and u is distributed uniformly. Which would imply g of u is just 1. So the PDF for x is simply given as del u by del x mod, which is del of fx by del x mod, which is nothing but f of x. So if G of u is a uniform distribution, then PDF for x is fx as desired. The difficulties with this method are integrating f of x to obtain capital F, the cumulative density function, and inverting the cumulative distribution to obtain f inverse of u. But if this can be done, then this is usually the best method. Now note, if capital F is not 1 to 1, then we define x equals f minimum inverse of u, which is the minimum of x for which f of x is greater than or equal to u. If we discuss the same methodology for discrete PDF, then this method can always be used since the cumulative distribution function is always easily calculated. So the probability of x equals xk just f of xk, and the CDF fk is the probability that x is less than or equal to xk, which is the sum from I equals 1 to k of xi. Now taking u to be uniformly distributed, between 0 and 1, the probability fk minus 1 less than u less than fk is the integral from fk minus 1 to fk for du, which is just fk minus f k minus 1 is given as small f of xk. To generate a point, what we need is to first generate ui as a random number between 0 and 1, and then find k such that ui lies between fk minus 1 and fk. then xk is the desired value of x. There is the second step, finding the value of k, which can involve a lot of steps. Normally one can save computer time by starting the comparison somewhere in the middle of the x range. Let's say at the mean or the mode, and then working up or down in x depending on u and fk. This is of interest not only for situations with a discrete PDF, but also for cases where the PDF is continuous but not known analytically. The resolution function of an apparatus is often determined experimentally, and the resulting PDF is expressed as a histogram. And lastly, we come to what is known as composite method. So it may be advantageous to decompose the desired PDF into a sum of PDFs which are easier to generate. So fx is sum over fk's of x. If we define alpha k as integral from a to b of fkx dx divided by the sum over all such integrals, then sum over the alpha is equal to 1, and an individual alpha k is the fraction of the points to be generated according to fk. In generating the points, we regard the index k as a discrete random variable with probability alpha k. We first generate a random number u from the interval 0, 1 and then use it to select k. Then we generate a value xi according to fk of x using one of the previous methods. Now let's look at an example. So it's a demonstration of the above methods. Let's say we take the PDF fx equals 1 plus x square. That must be noted. So we take it in the region from -1 to 1. It must be noted that this fx is not normalized. We could of course normalize it, but for the purposes of the current discussion, it's not necessary. Now this could of course correspond to some angular distribution with x equals cos theta. Now, first of all, if we look at the weighted events, and this is quite trivial, we generate xi as a random number between -1 and 1 and assign it weight wi equals 1 plus xi square. In the rejection method, we have f max equals 2, a equals -1, b equals plus 1. So we can generate xi as a random number between minus 1 to plus 1, which is equivalent to generating a random number between 0 and 1, multiplying it by 2 and subtracting 1 from it. Similarly, we generate Ri as a random number from 0 to 2, and this is again the same as generating a random number between 0 and 1, multiplying it by 2. And then the criteria for rejection is that we reject the point if Ri is greater than 1 plus xi square. So the efficiency of the generation is given as the ratio of these two integrals. So the efficiency comes out as 2 by 3, which implies 1/3 of all points are rejected. In the inverse transformation method, we have f of x is an integral from minus 1 to x, 1 plus x squared dx, which tells us that f of minus 1 is 0 and f at 1 is 8 by 3. So that's why we generate u as a random number in the interval 0 to 1, and then 8 by 3u is uniformly distributed on f of minus 1, f of plus 1. The corresponding value of x is a solution of this equation. 8 by 3u equals fx. This solution which comes out to be A is 4u minus 2 plus s cube, B is 4u minus 2 minus s cube root. S is the square root of 1 plus 4 times 1 minus 2u square. So this requires calculating 1 square root and 2 cube roots per point. Coming to the composite method, So we write fx as the sum of simpler functions. So in this case the choice is quite obvious. The integrals of these functions are easy to calculate. So we want to generate from FA with probability 2 by 2 plus 2 by 3, which is 3 by 4. From FB we want to generate with probability 1 by 4. So the first step is to generate V, which is a random number from the interval 0, 1. If V is less than or equal to 3/4, we generate from FA. What we generate is UI, a random number between 0, 1. Xi is given by the relation 2UI minus 1. If V is greater than 3 by 4, we generate from FB. And this we do either by the rejection method so xi equals twice of the random number from the interval 0, 1 minus 1, and ri equals a random number from 0, fp max, which is nothing but a random number from 0, 1, because fp max is 1. And we repeat until we find a point for which Ri is less than or equal to xi square. Now the efficiency comes out to be 1/3 for points generated here, which is 1 by 4 of all the points generated. The efficiency was 1 for the points distributed according to FA. So the net efficiency is 1/3 of 1/4 is 1 times 3/4, which comes out 5/6, which is a small improvement over the 2/3 of the simple rejection method. The same thing can be done by the inverse transformation method instead of the rejection method. So phi of x, the cumulative distribution function. It's an integral from -1 to x. Basically gives x cubed by 3 plus 1 by 3. We evaluate fb at -1 equals 0 and fb at 1 is 2 by 3. So we generate ui, which is a random number, from the interval 0, 1. And then xi, the solution of this equation, 2/3 of ui equals xi cubed by 3 plus 1 by 3, which basically implies xi is 2ui minus 1 cube root. Now here we only have to calculate one cube root, and that only for 1/4 of the events. That's why this method is 12 times faster than the simple inverse transformation method. So as you can see, for this example, the composite rejection method turned out to be the fastest. The simple rejection method only slightly slower. The composite inverse transformation method was much faster than the simple inverse transformation method, but still much slower than the rejection method. And these results should not be regarded as general. Which method is faster depends on the function f. One final point that we want to discuss is the Gaussian generator. The Gaussian distribution is one of the most important in physics and statistics, and many methods have been proposed to generate normally distributed points. So by the central limit theorem, the average of a large number of random variables distributed according to almost any PDF will be normally distributed. In particular, for n random variables, ui, which are distributed uniformly between 0 and 1, the quantity g, which is sum from I equals 1 to n of ui minus n by 2 divided by the square root of n by 12 is approximately distributed as normal distribution with random variable g, mean 0 and standard deviation 1 for large n. While simple to program, this generator is not particularly fast and has the feature that the trails are truncated at plus minus n sigma, which is usually undesirable. So if the absence of long tails is tolerable, this method is usually satisfactory for as few as n equals 12, where g reduces to Another disadvantage of this method is that it puts severe requirements on the correlations between successive points of the random number generator, in particular on correlations within groups of n successive values of ui. Now, a word of caution is appropriate for those who have noticed that instead of summing 12 ui and subtracting 6, what we could have done was used g minus, which is a sum that goes from 1 to 6, and then basically subtracted either 6 of those. But if one tries to save computer time by generating both G plus and G minus with the same 12 values of UI, the problem arises is that G plus and G minus are highly correlated in that case. So since the Gaussian PDF cannot be integrated in terms of the usually available functions, it is not straightforward to find a transformation from uniformly to Gaussian distributed variables. However, there is a clever method to transform two independent variables so u1 and u2, which are uniformly distributed on 0, 1, two independent variables g1 and g2 are normally distributed with 0 mean and unit variance. This transformation has the form g1 equals cos 2 pi u2 times the square root of minus 2 log u1. g2 is sin 2 pi u2 with the square root of minus 2 log u1. Now this method is exact, but its speed can be improved upon by effectively generating the sine and cosine by rejection method. So basically we generate uniform random numbers u1 and u2 on 0, 1. Then we calculate r square equals 2u1 minus 1 square plus 2u2 minus 1 square. If r square equals 1, if r square is greater than 1, then we reject u1 and u2 and go back to step 1. Otherwise, we define g1 equals 2u1 minus 1 times minus 2 log of r square by r square, and g2 equals 2u2 minus 1 minus 2 log of r square by r square. This saves the time of evaluating a sine and a cosine at the slight expense of rejecting about 21% of the uniformly generated points. So this is all that we wanted to discuss in the context of Monte Carlo simulations. Next time, we will dip our toes in the concepts of statistics.